Welcome back, everybody. So for folks playing along at home, Max, Grace, shout out. Um, I'm up at the front table, not up at the board. I'm mirror opt into both. Apparently, I'm not. Come on, play. There we go. We good now? I'm gonna shut the door. And this is going to be mainly done on your computers. So we all have our computers out here. So let's think about what we did in section 4.5. In section 4.5, it was all about like the culmination of everything that we learned throughout our high school careers about graphing functions, right? We talked about domain, we talked about intercepts, asymptotes, derivatives, concavity, inflection, everything, right? And it was all about how do we graph by hand. This section is all going to be how do I work with technology? How do I work with like a graphing system to kind of, you know, on the complete opposite side of the spectrum? How do I take what I know about calculus and pair it with like Desmos basically to really understand the relationship between the graph of f prime and f double prime? That's really what we're going to focus on today. So as you'll notice here on the assignment in Canvas, I'm on section 5. Why am I all the way back there? Modules. Okay, here we are. Chapter 4, section 4.6. Let me open this in a new tab here. There are only 4 homework questions. Page 392, numbers 1, 2, 4, and 6. Okay? For each of these homework problems, you're going to create like a digital homework assignment where I'm going to ask you to like screenshot how you graphed it in Desmos and explain. You can either type or handwrite. Explain what the graph means, what f prime means, how does it relate, intervals of concavity, intervals of increase, decrease, all that fun stuff that we did on paper without our computers or calculators. We're going to do with a computer. And hopefully we can see a correlation and really appreciate all the work that the scientific calculator is doing for us, or the graphing calculator is doing for us. So for each of these problems, you should create a digital homework with screenshots of your Desmos graphs. I do say on there, provide the written work for showing all the derivatives. I do want you to write out showing the derivatives. I do make an exception for that. You do not have to find the double derivative on number 4. It would be a beast. So I kind of let you not do that, but I'll show you how to still graph it in a second. And I'm going to have you showing screenshots of f prime, and f double prime, and revealing all the important points. And estimating all of the stuff that we usually handwrite out: intervals of concavity, intervals of increase, decrease, extreme values, inflection points. Okay. Now, how you do that is really kind of up to you. I'm going to show you how I would do it up in front of you today. So let's take a look here. The method we used to sketch curves in the preceding section was a culmination of much of our study of differential calculus. The graph was the final object that we produced, right? That was our outcome. The graph was the outcome. In this section, our point of view is different. We flip it. We start with the graph. We start with f, and then we see, okay, what can I say about f prime, f double prime? What are my intervals of concavity? What are my intervals of increase, decrease, and all that stuff? So we're kind of flipping what we did last section. Last section, we started the equation, and the end result was the graph. This section, I start with the graph and end with all of the important pieces, all of the work, basically. The work really is the solution. We use calculus to make sure that we reveal all the important aspects of the curve, and with the use of graphing devices, we can tackle curves that would be far too complicated to consider without technology. This is actually going to allow us to find all of those important pieces. This is going to allow us to find all of the important pieces of very difficult problems. Very, very difficult problems that we would have no chance of finding the derivative and graphing if we were to try to do it by hand. Okay? All right, so let's take a look at example 1 here. I would like everybody to go to now the book. If you look in the book for any of these sections, it's going to assume that you're using a TI-83. Okay. I am saying we are advanced beyond that because this book was written 10 years ago, and I don't even think Desmos was around back then. So I would like everybody to go to desmos.com. Almost, nope. Desmos.com. It's going to bring me desmos.com/calculator. Even if you just go to Desmos or if you just Google it, you want to just click on this graphing calculator here. Okay. I'm going to bring it out. Bring it out. There we go. All right. So here's our first example here. Graph the polynomial f of x. Use the graphs of f prime and f double prime to estimate all maximum and minimum points and intervals of concavity. So basically, do all of the work, but start with the graph. Okay, so let's just graph it and see what happens. Okay. I'm going to split screen this here. I'm going to hide this. I am going to graph. The nice thing about Desmos is you don't even have to do like an f of x equals or a y equals. So 2 x to the sixth. To get up into the exponent, remember you can do shift 6 to get up into the exponent. And then just to drop down, you just arrow down. Plus 3x to the fifth. Plus 3x cubed. Minus 2x squared. Now, this is going to be a weird section because like there's nothing really to hand write down for a lot of this stuff. Okay? A lot of this stuff is working on your computer. So not a lot of notes to take, not a lot of actual handwriting to do. It's mainly just work on your computer. All right, so there's f. There's our function here. Let's kind of analyze what's going on. Now, the nice thing about Desmos is that when I'm zooming in and out here, if I click on that function and if I have it active, it's going to give me all of the important points as little like suggested points to click on. Like I can reveal all of these points and see what they actually are. Now, I see this minimum point down here. I see something going on in here. It looks like I've got a maximum value, a minimum value, and this point is actually one that I didn't really even need. That's an X intercept. I don't really care too much about the X intercepts, right? What I care about are the maximum minimum points. I care about where it's changing from increasing to decreasing. Like for our purposes here, I can see that if I want to estimate the intervals of increase and decrease in maximum minimum values, okay, minimum value, negative 1.616, comma, negative 15.326. Go with nearest thousandth, just like they do. Looks like 0, 0, and then 0.352, comma, negative 0.097. Now, that would be very difficult to find if we needed to find it using calculus. Could we? Of course. But this is the nice thing about using Desmos is that it's all done right there for us. Now, let's now integrate this with the derivative. Now, when I ask you to take screenshots, I'm going to screenshot this real quick. When I ask you to take screenshots, see, I have a nice little screenshot tool. But what I would suggest you do, because you're going to be putting it into like Word documents or whatever, and I really don't care how you create this thing. You want to make a Google Doc, you want to make a Word doc, you do whatever you do, okay? Here's what I would do. I would make a Word document and screenshot into the Word document. There's a couple of different ways to do that. You could use the snipping tool, okay? I just searched for snipping tool. That'll do it, okay? And then if I just do a new snip, like if I go here, have my snipping tool here, I'm going to do new, and then it's going to highlight it. It's going to like gray out the back screen here, and I'm going to say, okay, I only want this. Boop. And that's going to, see, this is the snipping tool window. I can just right click and copy this and paste it to wherever it needs to go. Okay, so I would use the snipping tool. Know that if you are in a Word document, let me just open up a Word document as well. Hey, look, there's my background check. Look, that makes sure I'm not a criminal. Look at all my messy files. Healthcare book. There's my official transcript from Kent. You want to see all my grades? Let's see. I think I got all A's. It's taking too long to load. So in a Word document, you could also insert a screen clip here. If you go in the Insert tab, you could do a screenshot there. So if you were here with Desmos open, you'd have to have it open, bring up the Word doc, screenshot, drop it down, screen clipping. And then that's what I would need to see. Now, these aren't even good screenshots anyway, because I need to reveal all of the important pieces here. Okay, all of my maximum and minimum values. And I can use these to tell me when it's going to be increasing and decreasing. Like I can tell right now based off these values that the intervals of increase and decrease are, well, it's decreasing from negative infinity to negative 1.616, increasing from negative 1.616 to 0, decreasing from 0 to 0.352, and increasing from 0 to infinity, or sorry, from 0.352 to infinity. Okay. Now, how do I find my derivative then? And what does that look like on Desmos? Well, the nice thing about this, and how I'll be asking you to do it in your homework, is a lot of the derivatives are kind of simple to find. Like especially this is polynomial. Pretty easy to find. 12x to the fifth. Oh, no. Yeah, 12x to the fifth. What am I thinking? Drop it down, multiply. Plus 15x to the fourth plus 9x to the second minus 4x. That's the derivative, right? Drop it down. 6 times 2 is 12. Drop it down 1 to 5. 5 times 3 is 15. Drop it down to 4. 3 times 3 is 9. Drop it down to 2. 2 times 2 is 4. Drop it down to 1. So this is my derivative. Now, how does that relate? Now, remember that you can toggle the equation on and off over here. I don't have to like delete it. Like if I want my regular to go away, I just kind of click that, and that the regular function goes away there. Now, where should I click to find intervals of concavity? Or sorry, not intervals of concavity, intervals of increase and decrease. Where would my maximum and minimum values be on the first derivative graph? Where would I click? Like I had this, where was it? Oh, I didn't even reveal it. That point, that 0, the 0.3616, whatever it was. Where are those? They're my zeros of my derivative, right? So I should see a correlation between these values and where my maximum and minimum values occurred. Like for example here, let me reveal my initial. Do you see this piece here, this 0.352, that same x value? Oh, that's showing the cross point. There it is, 0.352. That minimum value is the X intercept of the derivative. Same thing here. It actually just goes through 0, 0. This 0, 0 is a maximum value because it goes through the x-axis on the derivative. Look right here. Negative 1.616. That is the x value of this guy all the way down here. You see that? That's the connection that I need you to see, and that's the connection that I need you to screenshot. So like, here's what I'm going to be doing. I'm going to say, okay, screenshot your original with all of these points. Okay, so I want this, this, and this, right? Those values. I'm going to go in here and do it to Smart Notebook because that's how I save my notes. Come on. Wake up. Here it goes. Oh, get out of here. So this is one graph that I need to see on your document, right? I'm going to send it, keep it to the same page. And then, kind of got distorted there. Whatever. I need to see the same thing, but now I want to see them as zeros of your derivative. Okay? So like here, I need to see all of this. And your job is to explain how those two images relate to one another. We see the negative 0.616 here as a minimum value and a negative 1.616 here as a zero of the first derivative. Now, let me ask you this. If I'm looking at my first derivative, where should I find the intervals of concavity? If I'm looking at my first derivative, where should I find my intervals of concavity? Does anybody know? Where would I find them? Boop. Boop. What did I highlight there? The maximum and minimum values of my first derivative. Because technically, this is where the slope of that derivative equals 0, which is essentially the double derivative. Let's calculate that again. So bring down the 5. That's 12 times 5 is 60x to the 4th plus 4 times 15. Isn't that 60 as well? 60x to the 3rd plus 18x minus 4. Okay, so let me turn off my single derivative. I'm going to turn off my double derivative, and I'm going to reveal these 2 points and screenshot that. Okay, I'll send it to a new page now. And I see those values. See, this is telling me that my intervals of concavity should be from negative infinity to here, right? And then to there. Let's see if that actually exists. Look at those x values. Yeah. Are those the same? I hope I calculated them right. Yeah, negative 1.233 and 0.193. There it is. Okay. And that's another screenshot that I need. I need the zeros of the double derivative because that is where the intervals of concavity would end up. Okay. So you're basically giving me all of the information that we had to come up with paper pencil in the last section. You're just giving it to me using technology. You're using your Desmos to tell me, okay, this is where the intervals of concavity are. This is where, this is where the intervals of increase, decrease are. There's where my maximum and minimum values are. Okay. So what do I need? I need screenshots of all of those. And then I need an explanation. I need to see all of the work there. Now, again, you can type up all of that stuff or you could handwrite. I really don't care. I just need it in one document for your homework. Okay. So let's do another one. Shall we? I do not need this. Like, this looks like a mess to me, right? I do not need all of them shown on the same thing. Okay. Now, what is kind of cool is this. If I'm on my double derivative, this negative 1.233 and this 0.193, do they truly show up as inflection points? Now, am I going to see that? Like, does Desmos actually produce the inflection points like as clickable points? No, but I could kind of estimate, okay, negative 1.233. Let's look back at my original. Negative 1.233, somewhere around right there. Is that a place where it goes from concave upward to concave downward? Yeah, about right there. Maybe a little further this way. About right there is where it goes from concave upward to concave downward. And then there's another spot where it goes from concave upward to concave downward, somewhere like really close in there, which makes sense because look at the zero of my double derivative right there, 0.191. Okay? Let's do another one. Let's do something real funky. There's my grades. What you're doing right now? No. I'll need you to do this for the homework assignments. Let's do a real funky one. Let's do a trig one. Ooh, yeah, that one. That one's a good one. Because, let me ask you this. This would kind of be pretty nasty to find the derivatives of, wouldn't it? Because I've got chain rule in there. I've got chain in a chain. Because I see I could find the derivative of sine. And then I'd have to take the derivative of the inside. But look at the second sine. Sine 2x, I've got to do another derivative in there, right? I could do that. I guess we could compute the single derivative. The double derivative would be very nasty. But let's take a look at this. Let's graph this. Now, it only wants it from the interval of 0 to pi. Okay? So let's graph it. It was sine, come on, split screen. Sine x plus sine 2x. Sine of x plus sine 2x. Okay. This is what we have. So what I'm looking at here, I'm only looking at it from the interval of 0 to pi, right? I really only want to look at it from 0 to 3.14, okay? Now, where would that be? That's somewhere around right here. Oh, look, there it is. Man, Desmos is nice. Look at that. They even give it in terms of pi. Are you kidding me? Look at that. So nice. So I'm going to kind of just like zero in my graph right to there. Now, what do I have here? Look at what I got. Looks like I've got a maximum value, a minimum value, a maximum value, a minimum value. Whoa, that's a lot. I've got 1, 2, 3, 4, 5 maximum or minimum values just in this little period from 0 to pi, just there, okay? Now, that means, what does that tell you about your derivative? That tells you that the derivative is going to have zeros at every single one of those locations. Now, Desmos, man, whatever money you're paying your programmers, it's not enough. Because look at this. What does that mean? What does that symbol mean? D over dx. The derivative. Boop. Boop. Copy. Control C. Control V. Are you kidding me? So I could just do that? Look at that. Okay, so what was it? What do I see here again? 1, 2, 3, 4, 5 zeros from 0 to pi. Look, they match up exactly to my maximum and minimum values. I mean, think about how difficult this would have been to find all those critical points. That would suck, right? And you know what else I could do? Let me hit arrow down here. D over dx of, copy, paste. There's my second derivative. Now, I'm seeing a big jumbled mess right there, though. Let's take that out. 0 to pi. You know what all these zeros are? Those are inflection. What is that? Oh, that's at pi. Those are inflection points. I have 4 inflection points just from 0 to pi. Right? 4 inflection points just from 0 to pi. So here's what I would need for this. I would need to see a screenshot of the regular function with all of the maximum and minimum values revealed. One screenshot there. Then I would need a screenshot of all of the zeros of the first derivative, showing that those x values are exactly the same as the x values of the minimum and maximum points. This will also tell me my intervals of increase and decrease, right? Then I need a screenshot of, let me undo, redo. I need a screenshot of the maximum and minimum values of the first derivative because those x values are the intervals of concavity. And I need to take a screenshot of that and show the zeros of my second derivative have those exact same x values. Okay? Now notice again, all of these x values, 0, 0.796, 1.301, those are all inflection points. Those are all inflection points. Let me go back to my original, right? So say this first one, 0.796, 0.796, 0.796. Where are you at? 0.796, right around there. Is that an inflection point? Yeah, that's going from concave downward, and then it goes concave upward. I mean, it's only a little bit. If I zoom in, I can see a little bit better. But right there, that's an inflection point, going from concave downward to concave upward. And I can see that again in another point. Look right here, 1.3009. 1.3009. Yeah, it looks about right there is when it goes from concave upward to concave downward again. See, what we're doing here is we're taking something that would be very difficult to find the derivative of, or even the second derivative of, and using Desmos to reveal all of those important pieces that we need to find. Okay? So, moral of the story is this. I need to see screenshots. I need to see basically two sets of screenshots. The first set is all about the intervals of increase, decrease, and the maximum minimum values. And you need to define what they are, okay? So, like for this one, I'll just go through it one more time. From 0 to pi, and I'll actually screenshot it so you see exactly what I want. This. Ooh, it's kind of a little messy. That's okay. So here's my first screenshot. These are all my maximum and minimum values revealed. Current page. Make it smaller because I can zoom in if it's in a document, right? Then I want that same thing, but I want them as zeros of my first derivative. They should be the exact same thing. Guess what? If they're not the exact same thing, you computed the derivative wrong or you've punched it in wrong, okay? So let me go back here and say, okay, screenshot this now. Send to current page. And then for all of this, I need an explanation of where my maximum and minimum values are, as well as my intervals of increase, decrease, right? That should be your x values right there. I should say, okay, well, then it's going to be increasing from 0 to 0.632, decreasing from 6.23 to pi over 3, increasing from pi over 3 to pi over 2. You get the idea. Okay. Then I come down and I do a couple more screenshots. This time, I want the concavity. So that means I need to find these points, right? Those points. I guess I could reveal 0 as well if I wanted to. I'm really just concerned with the ones that are happening within it for our purposes here. Send to current page. Here. So these are the zeros of my first derivative. My maximum minimum values of my first derivative, which are the zeros of, see, look at all those x values. Same exact x values. Here. Okay. Send to current page. And then I need an explanation of where are my inflection points and where are my intervals of concavity. Does that make sense? The solution, like the answers to the problem is really like the explanation of the graph, right? Like in the last section, we started with the equation and we produced intervals of increase, decrease, maximum and minimum values, intervals of concavity, inflection points. Now we start the graph and we take those points from the graph and produce that material. Does that make sense? All right. Those are the only two problems that I wanted to do with you guys. And then tomorrow, I'm actually going to let you just do this in class tomorrow. Okay. So I want you to be you don't have to do this tonight. You will have tomorrow in class to do this. I would expect you get this entire assignment done tomorrow in class because I want to help you through because using Desmos can get a little tricky. Okay. You know what I do want to do since we have just like 15 minutes left? I want to show you that if you're ever stuck on a derivative, like for example here, say I really did want to find, sine x plus sine 2x. Say I wanted to find that derivative. Looks really complicated, right? a lot of places where I could screw up, right? Let's find the derivative. Well, what's the derivative of sine? Cosine. Chain rule says I leave it the same, then I find the derivative of the inner multiplied to it. Okay, so times, what's the derivative of the inside? 1 plus cosine 2x times 2, right? Because I've got to do a chain rule in there. Now, you know what's really nice is that I could go in and say, okay, cosine of x plus sine 2x, and parenthesis 1 plus cosine 2x, and parenthesis times 2. Oh, something is wrong there. What did I do wrong? There's something weird. What did I do wrong? Cosine. Oh boy, what did I do wrong? Cosine 1 plus cosine 2x. Maybe my parentheses are just off. Maybe if I do, what if I do this? 2? Is that the same thing? No. It's very similar though. I've got the same x values. I don't know. Is it that? No. Oh. Is it this? No. Something's weird about this. But anyway, so obviously I made a mistake. I guess moral of the story is here, is that might have been, there's something weird going on. Did I screw up my derivative? Somehow, right? I must have done something wrong along the way because my derivative is not matching the derivative that Desmos is telling me that it is, right? So what you can do is kind of go back and check your answers. Like if you're ever calculating a derivative and you're like, this is not right, I don't know what I'm doing. Like for example, I'll show you a really easy example. If I have like 5x to the 4th plus 7x to the 3rd minus 2x to the 2nd, whatever. Okay, there's my original. What's the derivative of that? Well, 20x to the 3rd plus 21x squared minus 4x, right? If I was concerned that I got that derivative wrong, what I could do is come down here and say d over dx of, of my original. And these two statements should be the exact same thing, right? So if I go back here, I'm going to turn off my original. If I look, boop, 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 this is the exact same thing. So you can always check yourself. It's kind of like a derivative calculator almost. Yeah. All right. Just so you guys know, assessments wise, what's coming up. We are going to do a quiz over just sections 4, 5, and 4, 6. Okay. Just over sections 4, 5, and 4, 6. That's actually going to be next Tuesday. On Tuesday, you'll be all right. On Tuesday, I'm going to be giving you 2 graphing problems. 2 graphing problems. I'm not going to do anything crazy to you, but I'm going to give you 2 graphing problems, and it'll be just like what the homework was. Okay, that you will complete in class. Then I will give you something to do. I will give you basically what we did today. I will give you a function and ask you to graph it using Desmos and screenshot and show me all important points. That will be due at midnight that night. You don't have to do that in class. You can just get that done and submit it by midnight that night. So there will be 2 parts to the quiz. A part that you will complete just with red calculators in class, 2 graphs, done, turn it in. And then a part that you will do at home where you'll take a function, find the first derivative, second derivative, screenshot everything you need to, show me intervals of increase, decrease, concavity, inflection, maximum, and minimum. Make sense? Cool. That'll come next Tuesday. And then we do section 4-7, I think, and we have another quiz and then a test. All right. Let me turn off my video.